Okay, this is a nice feature article in Nature that just appeared a few weeks ago. I'm recording this in March 2025. This is about microplastics and how they affect our health. You know, microplastics are everywhere, including in our body. It's in the air, in water, and in foods, and also in our brain and so on. So here, they are in our kidneys, livers, lungs, and especially our brains. Researchers are scrambling to understand the effects of the ubiquitous little particles that we eat, breathe, and live among. So this article, obviously, feature articles tend to have lots of interviews of people who are working in this field, trying to understand the impact of microplastics on our health. And I'm going to keep it brief by just reading the quotes because they highlight the various issues that are involved. So let's start with the leading material. A sliver of human brain in a small vial starts to melt as lye is added to it. Over the next few days, the caustic chemical will break down the neurons and blood vessels within, leaving behind a grisly slurry containing thousands of tiny plastic particles. This is being done by toxicologist Matthew Campen, who has been looking at isolating and tracking microplastics, and his interest is not only in the brain, most especially in the brain, but he also looks at kidneys and livers, and brain somehow seems to concentrate it, but it's unclear whether it depends on how it got into the body and so on. They can do a lot of damage in the lung, for example, and we still don't know exactly what happens when it gets into the brain or kidney and liver. So he's at the University of New Mexico in Albuquerque, and he says he can isolate about 10 grams of plastics from a donated human brain, and these numbers have jumped up over time. And just to impress upon you, ocean is of course full of plastic, and there are the great garbage patch and so on that are famous for accumulating macroplastic that you can see from the satellites sometimes. But there are also microplastics down deep at 11 kilometers in the Mariana Trench, and it's of course in our food and water and the air we breathe. So detection is only the first step. Determining precisely what these plastics are doing inside the people and whether they are harmful has been much harder because there is no one microplastic. They come in various sizes, shapes, and chemical compositions, and each of these could affect the cells and tissues differently, and there is also no clear way to track nanoparticles. We'll see the size classes in a minute once they get assimilated into the cell, right? So it can go through the system, let's say, to some extent. In the lung it can cause inflammation and so on and so forth. Kidney and liver, what does it do? In the brain, what does it do? It's unclear, but we'll see one example of how heart patients may have been affected by these, at least in a correlation sense. So Campen's beige sludge comes into play because despite the microplastics ubiquity, it's difficult to determine which microplastics people are exposed to, how they are exposed, and which particles make their way into the nooks and crannies of our body. So Campen works with cadavers. Morbidly speaking, the best source I can think of to get good relevant microplastics is to take an entire human brain and digest it. So he puts lye and then melts it away, right? So world is of course hungry for data, and there are negotiations going on under the UN to ban plastics production, but there is no cookbook at this point. There is no manual or standard operating procedure, says Kathleen Egan, a cancer researcher at Moffitt Center in Tampa, Florida. We are having to make them up as we go, and it's a process. So basically, people have been doing it with different methods, and negotiations haven't materialized yet, but there are signs that the scientists are ironing out these kinks of different methods and different types of plastics. In labs they are using simple pure microplastic spheres, which is not what people are exposed to, and so on and so forth. Okay, plastics production, which began less than a century ago, reaches an all-time high each year, and the material takes hundreds if not thousands of years to degrade, which will create trillions of microplastics in this process. There are microplastics everywhere, says Bart Coleman's, an environmental chemist at Wageningen University in the Netherlands. I don't know how it's pronounced. We cannot run away from them, says Coleman's. It's all piling up though. So microplastics was coined only 20 years ago, but Martin Wagner, a biologist at the Norwegian University of Science and Technology in Trondheim, says it's a young field in terms of gauging their effects on human health. Campen's team, we mentioned him before, has already found grim results. As the number of plastics created has increased sharply, so too has the concentration of microplastics found in the brain, liver and kidneys, according to his group's results published in Nature Medicine this month in February 2025. On average, microplastic levels were about 50% higher in the brain samples from 2024 than in 2026. So just in 8 years, it has jumped 50%. The brain samples contained up to 30 times more microplastics than samples from a person's liver and kidneys. So somehow the brain is human body is finding a way to amplify the concentration or accumulate them in the brain compared to liver and kidneys. Another study published in January of 2025 might offer clues as to how the particles congregate. Researchers fed mice water laced with microplastics and tracked the movement of the particles through the bodies of the mice. Researchers found that the plastics were gobbled up by immune cells and ended up piling up in and blocking small blood vessels in the brain. So we are happy to torture other animals for our own health, protection and learning about how to protect ourselves, etc. But nonetheless, that tells you something about why the body is reacting in a certain way, because unlike the pathogens where the body decides to get rid of it by diarrhea or vomiting or fighting it with autoimmune diseases or whatever, I think autoimmune is not that one, never mind. So it's fighting ghosts in that case. So immune cells probably don't know how to react to plastics, because plastics are probably not multiplying in the body, and if foreign body begins to multiply, then the immune cells may react very differently. What plastics do to human organs is subject to intense study though. When scientists add microplastics to human tissue samples in the laboratory, it can result in cell death, immune reactions and tissue damage, and hundreds of studies have exposed animals, mainly aquatic organisms, to microplastics and found that the particles can clog their guts and hinder their ability to reproduce. On the basis of these findings, researchers suspect that these particles could be linked to cancer, heart and kidney disease, Alzheimer's disease, or fertility issues in people. For example, turtles which eat jellyfish in the ocean mistake plastic for jellyfish. They eat them. Unlike jellyfish, the plastic doesn't get digested, they don't feel hungry, and they end up starving to death. But there is no evidence yet that microplastics directly cause poor health in humans, only data that show a link. So people have had heart data, so they found that those who did have a lot of micro and nanoplastics in the main artery were 4.5 times more likely to experience a heart attack, a stroke or a death in the 3 years after the surgery than were those whose arteries were plastic free. But of course, as the authors themselves point out or acknowledge, the presence of plastics might be a correlation with other factors that would influence health, such as diet or socioeconomic status. So causal links to plastic has not been made yet. Shifting science then, the field has grown in the past decade. For example, in 2014 there were only 20 papers published that included the keyword microplastics listed in Elsevier's Scopus database. Nearly 6,000 were published in 2024. That's a massive jump. The US National Institutes of Health, NIH, issued its first grant with the word microplastic only 7 years ago in 2018. Since then, the agency has funded more than 45 projects, but by now NIH is being dismantled, so we have to see how that turns out, right? Samples of types of microplastics that have been found in the Atlantic Ocean here, you can see some are fairly large and you can see them with your eye, and a lot of the smaller ones are ending up with the fish. And of course, imagine a big animal, a mammal like a whale that opens up its mouth and gobbles up lots of water to eat what's in, is going to take up a lot of these particles as well. But as money comes in and interest grows, researchers are still developing methods. This burst of innovation is exciting, says Phoebe Stapleton, a toxicologist at Rutgers University in Piscataway, New Jersey, who studies the effects of plastics during pregnancy. But it also means that each team of scientists is developing and using different analytical approaches to detect and characterize microplastics, and there haven't been many studies analyzing each method's reliability or validity. But it's clear that these are getting into the fetus and then taking up more space, as we'll see in a minute. For example, many studies use the pristine microplastics such as small spheres that are not representative of the diversity of plastics found in the environment. Is that really useful or not? We defend our areas like crazy, says one of the researchers who's this? Dun, 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 dun. Never mind. So idea is that everybody is working in silos, and even though each one is a good research by itself, they are not able to be compared directly. So plastics might also affect each organ or cell type differently. For example, a sharp microplastic fragment might be more damaging in the fragile lung environment than in the throat, for example. The dose, of course, matters, as well as the route of ingestion, as says Alison Elder, an inhalation toxicologist at the University of Rochester Medical Center in New York. The inhalation route is a major concern because if inhaled plastics can get into the deep lung and cause an inflammatory reaction, they don't need to go anywhere to cause health outcomes. Inflamed lungs can make you very, very sick. Okay, so there are other comments from Stapleton saying, while field develops tools and works as the field develops tools and works out the strengths and weaknesses of each one, it will be important for researchers to use multiple methods to confirm the characteristics of the particles they are finding, Stapleton says. So there is also the nano, so micro to nano then. Of particular concern are the smallest of the plastics that get inhaled and ingested, says Stephanie Wright, an environmental toxicologist at Imperial College London. Particles of less than 1 micrometer across are called nano, but some people argue that it should be much smaller at 0.1 micrometers. We will see the scale in a minute. Nanoplastics might be taken into cells in which the body doesn't have the established mechanism to digest or expel them. Okay, so some of the larger ones can pass through the digestive system and are excreted. So if it just passes through the system, or if it just sits quietly somewhere, it's one thing, but it causes inflammation and clogging of the arteries, etc., then it's much more problematic. Stapleton and her colleagues, for example, have found that during pregnancy the placenta does not serve as a barrier to nanoparticles in rats, and that nanoplastics cross from the mother to fetus and are quickly dispersed in the fetal tissue. It will be important to understand what the particles are doing there, Stapleton says, especially because they take up a disproportionate amount of space in a fetus compared within a fully grown adult. So here is the scale just quickly. So nanoplastics and microplastics, you're going from 10 nanometers to 100 nanometers, 1 micrometer to 100 micrometer, and then several millimeters out to 10 millimeters. If it's less than about 1 micrometer, then particles can cross the blood-brain barrier. If it's less than about 10 micrometer, then it might cross into the cell. And then human macrophage scale is here at around 20 to 100 micrometers, and then alveoli, you can look up what those are. Asbestos flakes that we worried about so much that people were breathing and got really sick, ranged from 100 nanometers to 10 micrometer. Sand and sediment go from 10 micrometers to millimeters. You can obviously see most of them. PM 2.5 starts at about 100 nanometers. Of course, it goes to 2.5 micrometers, and PM10 is of course 10 micrometers, and so on and so forth. Okay, so it gives you a sense of the biological objects, non-biological particles in blue here, and tools used for analysis include pi GCMs. The cost is also mentioned, FTIR, optical microscope, naked eye if it's large enough, micro-Raman spectroscopy, so black or dark colored particles cannot be identified in this method, but you can see the numbers for the diagnosis, which of course puts a severe limit on how much people can do, right? So using most microscopy methods, you can't see particles less than about 250 nanometers, and those are the most important to look at to quantify the dose that accumulates in the tissue, Elder says. Contamination is also a problem because the tools used to analyze these and detect these things and so on themselves have biological they themselves are made from plastics, so you can have cross-contamination. Researchers must characterize these background levels to distinguish the signal from the noise, says Egan, who obviously is working on this as well. With so many variables to consider, it's easy to get bogged down, Wagner says, but we need smarter approaches if scientists are to amass a body of evidence quickly. For example, scientists might group plastics and additives together on the basis of structure and use these groupings to predict their impact on health, he says. Developing these smarter approaches will require serious collaboration between the groups of scientists, obviously, and get out of the silos. And it's not just a matter of developing new tools, there's an element of infrastructure and expertise development as well needed. We need more interdisciplinary collaboration and workforce training as well. Okay, that's from Elder. Big decisions then. The dearth of data has made it difficult for researchers to communicate potential risks to the public and to policymakers. This is a familiar conundrum. Scientists have long contended with offering recommendations based on incomplete data for topics such as air pollution or smoking cigarettes. So now alcohol and cancer are being talked about a lot. Red wine was argued to be good by some, and then it was argued that they were sponsored by wine industry and so on, but now we are saying any amount of alcohol is bad for cancer. So does that mean you start banning alcohol before any solid evidence comes in, or you let people drink? So this is not an easy ethical question. But a wave of attention and worry about microplastics has lit a fire underneath researchers to seek answers urgently. When people ask me what they should do about microplastics, I feel like I should have some kind of a response. Stapleton says people are really interested. Okay, so we are producing massive amounts of plastics, which is going to more than double by 2050, 400 million tons each year, which is going to reach probably 800 tons. So it's better to cap these numbers before the impacts continue to snowball. This year is a pivotal one for global plastics governance. There has been some negotiations under UNEP, United Nations Environment Program in Nairobi, but the treaty hasn't been finalized yet. Talks so far have not yet yielded a treaty, but delegates are slated to reconvene later this year in 2025. Microplastics are only a small component of this global push, but the urgency has led some researchers to publicly press for policies to reduce plastic pollution. We are in this historic moment where we could get to an effective treaty, some of us have said. Now's the time that we need to work on this rather than sticking to writing our papers and grants, Wagner says. He worries that if the negotiations fail, it will be difficult to bring countries back to the table for decades. we have more than sufficient evidence to act. In other words, with everything we know, we can begin to make rules and regulations about plastic production and microplastics. Campan's tone deepens as he considers the implications of doing nothing. This is very visceral. We want to do more work on this, but it's very scary to think the concentration of plastics in my brain will go up several percentage points before we have the answers, he says. Okay, so it's a bit scary. So even though we don't have definitive answers on exactly what microplastic and nanoplastic is doing in our body onto our health, it only makes sense to look at the numbers and realize that this is a risk that we must deal with. Risk is always complex, and you can't wait for the final answers to be in before you take action. So that's where we stand. I'm going to leave it here, and then we'll come back to another health topic about how to cool sustainably with all the increasing heat waves in terms of duration, frequency, intensity, scale, etc. Okay, see you in the next podcast.